When I cut this particular solenoid, the length factor is decreased and the number of turns is also decreased. A magnet will always have a north and south poles, and the magnetic field lines will start from the north pole and end in the south pole. The electrical dipole kept in an electrical field, and we found out that to be U is equal to minus PE cos theta. So for the electrical field, we did a special case, that is when theta was equal to 0 degrees, 90 degrees and 180 degrees. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, Mysuru. So, we are going to deal with a new chapter here, that is magnetism and matter. That is a continuation of the topic moving charges and magnetism. Basically, we are going to dive deep into the world of magnetism and understand what magnetism is all about. So, this is actually a theoretical chapter which deals with the theory of magnetism and matter. So I won't be discussing everything in depth, as it is a basic comparison with the electric field and certain other topics we have already seen. So we'll be going a bit fast in this particular chapter because it's pretty much theory, but everything will be explained in detail. So what exactly are magnets? What is its specialities? We do know that a magnet is something which is made up of two poles. For example, this is a bar magnet, and we can clearly say that there are two poles to a magnet. One will be north and one will be south. So we have already studied about magnets in the previous lessons and in the previous minor classes. So I won't be re-explaining everything like poles repel each other, unlike poles attract. Those sort of things I won't be repeating here. So please recollect all the memories you have of this particular magnet. So if you remember the previous chapter, we said that a current carrying solenoid, imagine that this is a current carrying solenoid. If this is a current carrying solenoid, then we discussed that this particular bar magnet behaves like a current carrying solenoid, which means it will have the same properties of magnetic field and it will have the same effects when we deal with solenoids. That is, if I cut this particular solenoid in half, I told you that the magnetic field also will be reduced. That is, when I cut this particular solenoid, the length factor is decreased and the number of turns is also decreased, which means that the strength of that particular magnetic field due to that current carrying solenoid is also reduced. Just like that, we can also say if this is behaving similar to a tightly wound current carrying solenoid. That is, the bar magnet is resembling a tightly wound current carrying solenoid. If the bar magnet also is cut, let's say it is cut into two pieces, what will happen is that the magnetic field strength of that particular bar magnet will also decrease. So remember, a current carrying solenoid and a bar magnet will be behaving mostly similar to each other. Not just while we are cutting it, but also in the magnetic field strength and the magnetic field lines. We know that for a current carrying solenoid, the field lines will be traveling like this, that is straight through the middle and around in a closed loop. Just like that, the bar magnet will also have a field line which is traveling from north to south around the magnet, and inside the magnet it will be traveling from south to north. Now, why did I just explain this? Because we are going to compare and study. We are going to do a comparison study between the magnetic field and the electric field. So we know that the electromagnetic spectrum is complementary to each other. That is, the magnetic field is complementary to the electric field. Many things are symmetrically same in both the fields. So we'll see and decide how they are similar, what are the differences, and how we can actually compare and study them. So magnets. So what are the basic properties you all do know about magnets? So as you all know, there are two poles, there is north pole and south pole, and the second thing you already know is that there are magnetic field lines that start from the north pole and end in the south pole. Those are the basic things everyone will remember. But what are the other things we have to keep our focus on? So one important thing is that while there is a magnet in existence, that is, if there is a magnet present, there will always be magnetic field lines that will form continuous loops. That is, the lines of force, that is the magnetic field lines, will always start from the north pole and they will always end in the south pole. Why I said this is because if you remember the electric field, then we know that we can have a standalone positive or negative charge. That is, we can have either positive or negative charge in a given space, which means that the field lines will emanate out of that particular source charge, or the field lines will come towards the particular source charge. So they can actually have field lines actually coming in towards the source charge, or they can have field lines leaving from the source charge to infinity. That is no problem. But for a magnet, it is said that always it starts from the north pole. That is, the magnetic field lines will start from the north pole and it will always end in the south pole. So that is one thing you have to remember. And the next thing is that they will always form continuous loops. That is, they will always create closed loops. If a magnetic field line starts from the north end, it will always end in the south end. To make it more clear, when you draw a bar magnet, this will be the shape of the bar magnet. And let's say this is north and this is south. So what we know is that the field lines will start from the north pole and it will travel towards the south pole. But one thing you have to understand is that magnetic field lines do not actually start from the north pole and end in the south pole. They form a continuous loop, which means that essentially there is no starting point and no ending point. They are just continuous closed loops, which means here, let's say the direction of the magnetic field is from north to south, but inside the magnet, it is actually from south to north, which means the magnetic field lines traveling will continue until they reach their starting position, forming a closed loop. So you have to understand that we are saying that the magnetic field lines start from the north pole and end in the south pole. But in actuality, what is happening? The magnetic field lines is going in a continuous loop. The direction just so happens to be north to south outside the magnet and south to north inside the particular magnet. So that is the second property, that is, they always form closed loops. Not just closed loop, it is closed continuous loops. So you have to remember that, that is closed continuous loops. So they don't just break and then come back around. It's not like they'll go here, go someplace else and comes around. It's like they always form closed loops. There is no starting and basically no end. But just for direction sense, we'll say that it starts from the north pole and end in the south pole, and inside a bar magnet, the field lines travel from south to north. The next thing is that field strength. So how exactly do we understand field strength? So let's take a basic example anyone can do. If you bring a bar magnet and if you bring a nail or any magnetized object near that particular bar magnet, we can see that the strength is experienced near the poles compared to the sides. That is, imagine that this is a particular bar magnet and this is a nail. So I try an experiment where I try to bring a nail closer to the magnet. So as I get closer, I feel the force of the magnet trying to pull the nail towards it. And the important thing is that when I bring it through the sides, the attraction is not too much. But when I try to bring it near the poles, the attraction is more. That is, I feel a stronger pull or push in the polar region compared to the axial points. So why exactly does that happen? That is the reason of field strength, or simply the strength or concentration of field lines in that particular area. So we all know that the field line concentration actually determines the strength of that particular field, or simply if you remember the electrostatics, we know that the strength of flux will determine the strength of that particular field. So as there is more concentration of flux, or if more number of field lines are coming out through the poles, then we can say that the concentration of field lines are more in the polar region, which means it will have a more concentrated, strong field near the polar region compared to the sides. So that is why when you bring any magnetized object near the poles of a magnet, it will experience more of a push or pull. Or in simple sense, we can directly say that more the number of field lines, more will be the strength. That is, if I take a particular area here and a particular area here, the field strength will be more near the polar region just because there will be more number of field lines passing through here. And compared to this particular point, the number of field lines passing, there might be field lines passing, but comparatively, the field lines passing through that particular area will be less, which means that the strength of the magnetic field will be more near the polar region compared to the sides. Now, this is true for everywhere because as we decrease the number of field lines in a particular given area, the field strength decreases. So we can just say that more the number of field lines, more the number of field lines, more stronger the magnetic field ever will be. So it is stronger near the poles compared to the sides. And if you ever want to know what is the direction of the magnetic field at a given point, same like electric field, that is, we will draw a tangent in the particular direction or particular point which we want to know the direction in. That is, if we want to know what is the direction of the magnetic field at point P, what we will do is that we will draw a tangent and then we will get the direction of that particular field line. For example, here the direction of point P is given as such. So the next property is that if you draw a tangent in anywhere along the field, then that will give you the direction of the magnetic field at that particular given point. If you want to know what is the direction of the particular point P, then all you have to do is that draw a tangent along that, and that will give you the direction of that particular field line. And finally, again, a simple property you're all familiar with, that is the field lines never intersect with each other. Why? Because same reason, that is, if the field lines ever intersected, that is, if a field line passed through like this, the problem is that the tangent will always give you the direction. And if the field lines intersect, there will be a point where two directions or multiple directions will be possible at the same exact location in time and space. And that is just not acceptable. So these are the main properties you should remember. That is the basic properties. Magnet has two poles basically. A magnet will always have a north and south poles, and the magnetic field lines will start from the north pole and end in the south pole, and they always form continuous loops. That is, there is no break in between. They will start from the north, end in the south pole. Inside the magnet, they will start from the south and end in the north pole. So basically, they are forming a continuous closed loop. They have no beginning or end. And then there is the strength of the magnetic field. That is, if the field lines increase in a given particular area, then the strength of the magnetic field also will be increased. So if the field line strength or field line concentration is less, then we can clearly say that the strength of the magnetic field is less in that particular given area. And finally, if you want the direction, just draw a tangent and that will give you the direction of the magnetic field. And field lines can never intersect each other because multiple directions will exist in that particular point. So field lines will never intersect each other. Now, since you remember all the basics, let's dive into the chapter. That is, what happens when I try to measure the magnetic field at, let's say, point P at r distance or x distance away from a magnet. That is, what will be the magnetic field at point P? So if I try to measure the magnetic field at point P, that is the axial point along this magnetic dipole, that is north and south poles, what will be the magnetic field? Earlier your textbook had a long derivation, but now since we are comparing and studying, we already know that this particular bar magnet will be behaving like a current carrying solenoid. So it will be behaving like a current carrying solenoid, which means that we already know what is the equation for the magnetic field at point P, that is along the axial line at point P, x distance away from the center of a current carrying loop. Remember, a solenoid is just a current carrying loop repeating on itself. That is, multiple loops that is carry current. The n factor will be more. That is, here the number of turns is 1, here the number of turns is 1, 2, 3, like that. So if the number of turns increase for a current loop, we can say that it is a solenoid. If it does not increase and is just 1, we can just say that it is a current loop. So basically, I am asking you what is the magnetic field at the axial point for this current carrying loop. We already know that and we derive that particular result, and that particular result is also applicable for a bar magnet just because this particular bar magnet behaves like a current carrying solenoid, which means that this particular dipole, that is this particular magnetic dipole, will have the magnetic field along the axial point to be B is equal to mu naught divided by 2 pi into 2m divided by r cube, r being the distance. So we are trying to compare and study here that for a current carrying solenoid or just a current loop, the point P along the axial line was found to be mu naught by 2 pi into 2m divided by r cube. This was derived in the previous chapter. So this is the equation for the magnetic field along the axial point. And for a bar magnet also, experimentally we know that the magnetic field at point P is also given by the same equation, that is B is equal to mu naught by 2 pi into 2m by r cube. Remember here is that we are comparing magnetic and electric fields, which means that we are comparing a magnetic dipole and an electric dipole. We already know that for an electric dipole, the electric field is given by the equation E is equal to 1 by 4 pi epsilon naught 2p by r cube. So what I'm trying to say is that we already found out what is the electric field for an electric dipole in the first and second chapters, and we know that this is the particular equation denoting the electric field along the axial point for electric dipole. Now this is very similar to the magnetic field along the axial point for a magnetic dipole. So basically we are comparing NS. This is a magnetic dipole, simply a magnet. And here it is positive and negative. And negative. So we are comparing a magnetic dipole with an electric dipole, which means they have a similarity and we are comparing that. So here the constant we use for magnetism is mostly mu naught by 2 pi or simply mu naught, magnetic permeability. And here we are using the constant epsilon naught, that is electrical permeability. So here it is the constants we use for magnetism, here the constants we use for electrostatics. Mu naught by 2 pi, 1 by 4 pi epsilon naught. Here it is 2m divided by r cube, 2 times the magnetic moment divided by the cube of the distance between them. Here it is 2 times the electrical dipole moment divided by the cube of the distance between them. So here it is magnetic dipole moment, here it is electrical dipole moment. So basically they are behaving in the same manner. Remember, this is the axial point. This is the axial points, which means for the equatorial points, that is when we measure along this particular direction or this particular direction, that will also be comparative in nature. That is, if I get the equation for the equatorial field in the electric dipole scenario, I can say that it will be equal to 1 by 4 pi epsilon naught p by r cube. This was the equation for the electric field along the equatorial point for an electric dipole. But for a magnetic dipole, it will be very similar. If you try to find it, it will be equal to mu naught divided by 2 pi into m divided by r cube. So basically, it is a comparative study. Whatever we studied for the electric field, most of it is directly applicable in the magnetism case also. Why? That is because they are complementary fields. That is, the electric and magnetic fields are complementary to each other. They share a certain level of symmetry with each other. So we can say that they are complementary to each other. Electromagnetic fields. It was actually Maxwell who united these theories together and came out with a cohesive understanding of electric field and magnetic field. He clubbed it together and came out with the grand unified theory, that is electromagnetic fields. So this comparison is much easier for us now because of Maxwell. So as I told you again before, it is just a comparative study. So what did we actually do for the electric dipoles? We'll try to attempt and do it same here for the magnetic dipoles also. Magnetic dipole just means that it is north and south poles. So basically we found out what was the torque exerted by an electric dipole kept in an electric field, which means that we will find out what is the torque experienced by a magnetic dipole kept in a magnetic field, and then we'll find out what is the potential energy of that particular dipole. So we know that the things we have to do is that we have to consider a magnetic field which is uniform in nature. There we considered an electric field. Here we are considering a magnetic field. Then we are going to consider a magnetic dipole. Here simply we can say that we can just take a magnetic needle. Let's say this is a compass needle. Then one side will be north, the other side will be south. So basically it is also a dipole. So I'm going to keep that particular magnetic dipole or simply the compass needle in that particular magnetic field. Since it is kept in an external field, it will experience a torque which tries to push or pull on it. So if I place this particular magnetic dipole, that is north and south, if I place it here, it will experience a force, one along the field and the other one in the opposite direction of the field, which means it will experience a torque because the forces are equal but acting at different points in time and space. So it will experience a torque and it will try to spin through a small angle of d theta. We assume that and we derive the result just like we did it for electric dipole. So simply we will say that torque experience for an electric field was equal to Pe sine theta, or we wrote it as vector P cross vector E, and this was for the electric field. And similarly for the magnetic field, it will be equal to, instead of dipole moment for the electrical field, that is electrical dipole moment, we will have magnetic dipole moment. So we will have the magnetic dipole moment which is M. So M, instead of E, that is electric field, we have magnetic field here. So we'll write B, that is magnetic field, and here we have sine of the angle between them. So here also we'll have sine of the angle between them. So we can write it as vector M cross vector B. So this is the equation to find out what is the torque experienced by a magnetic dipole kept in a magnetic field. So again, it is just comparative study. Now, the second case is that we try to find out what is the potential energy of, let's say, the electrical dipole kept in an electrical field, and we found out that to be U is equal to minus Pe cos theta. So what will be the equation for magnetic dipole? That is the potential energy for a magnetic dipole kept in a uniform magnetic field. If it is minus Pe cos theta for electrical system, then we can say that it will be minus Mb cos theta for magnetic systems. That is, in order to find out the potential energy, we calculate the work done. We know that the equation for work is force times displacement, or in this particular case, it is the rotational sense of force, that is torque. So we can say that it is potential energy of magnetic field or magnetic dipole moment here. I'm not going to explain this even further because it was clearly explained in the electrostatics chapter and it is the same thing. So we are just comparing things here. So we can just say that the potential energy will be equal to integral tau d theta. Then we can say that the expression for tau or simply torque is given by M cross B or simply Mb sine theta. So we can say that it is equal to integral Mb sine theta. So here it is integral Mb sine theta. In the electrostatics chapter, we assume the angle to be from theta 1 to theta 2 and then we generalized it. Here we don't have to clearly do that because we already know the steps. So we are just trying to find out what is the integral form, and we find it to be m and b are constants, so it comes outside just like before. Integral sine theta, so integral sine theta is nothing but mb minus cos theta, or simply it is equal to minus mb cos theta. And we know that if the angle between two vector quantities is sine, then we can say it is cross product. Since the angle between two vector quantities here is cos theta, we can say that it will be a dot product. So we can write it as minus m dot b. So this is the potential energy experienced by a magnetic dipole kept in a uniform magnetic field at a particular angle. So if you remember, the potential energy for the electrical field was given by U is equal to minus Pe cos theta, or simply minus P dot E. Now we are comparing the magnetic potential energy experienced by a magnetic dipole kept in a uniform magnetic field, and we found it to be minus mb cos theta, or simply minus vector m dot vector b. So this is the equation to find out the potential energy of that particular particle. So we know everything, most of the things are a comparative study, apart from a small minor difference which I'll discuss very soon, that is monopoles do not exist for a magnet. That will be discussed very soon. But other than that, most of the things in this particular chapter is a comparative study. So for the electrical field, we did a special case, that is when theta was equal to 0 degrees, 90 degrees and 180 degrees. So just like that, we'll also find out what is the special cases here also, that is when theta is equal to 0 degrees, what will happen? What will happen when theta is equal to 90 degrees, and what will happen when theta is equal to 180 degrees? The results are also very similar, that is when theta is equal to 0 degrees, cos becomes 1, that is cos theta will become 1, then we can say that potential energy will be at its minimum. So when the dipole is parallel to the field, then we can say that potential energy is at its minimum. Already there is a minus sign here, just like before also. So we can say that the potential energy will be experienced minimal in that particular case where theta is equal to 0 degrees. So 0 degrees is done, and then what happens when theta is equal to 90 degrees? When theta is equal to 90 degrees, cos theta will be equal to 0, which means that there will be 0 potential energy as the dipole will be perpendicular to the magnetic field, hence the potential energy will be 0. And finally, when the dipole is at 180 degrees to the current magnetic field, then we can say that it experiences an unstable equilibrium. That is, it will be the most unstable point as it is facing the other way around. So we have to say that it will be the most unstable point. So 0 degrees will be the most stable point, and 90 degrees potential energy will be 0. And for 180 degrees, it will be the most unstable point. So these are the main things you have to remember. So in this class, it was just about discussing the basic properties of a magnet that you have to remember, and the comparative study, the nature of comparative study of magnetism and electric fields. So electric fields and magnetic fields have similar properties, have similar dynamics, so we can compare and study them. So I think you now have a certain idea how you can compare and study electric and magnetic fields, and this will be much more easier for you since you already know the chapter of electrostatics and electrodynamics. So I'll see you all with the next session where I'll introduce a new concept again, that is a comparative study. So I'll see you all very soon. Thank you.